Hi there! Welcome to the 11th episode of the Synth project, where we are going to build a synth together. Since I have received the PCB I designed for the VCO, I started immediately to work on the final assembly of it. In this video I will show you how to mount all the components of the VCO on the PCB, how to prepare the cables that need to be connected between the VCO board and the front panel, and how to connect them on the PCB side. Given the amount of components and cables, we need to be very careful and respect some simple rules that will make it easier to avoid mistakes. I also started working on the final touches of the front panel, and toward the end of the video I will show you how I decided to make the decals for it. I will of course put the PDF file for the decals in the zip file available on my website eleneasy.com. The link is available in the description of this video. And now let's begin. Here is the PCB for the VCO, and yes, it is unusually big for the projects you have already seen on this channel. Given the complexity of the PCB, I wanted to make sure that it reflected exactly the schematic I designed, and so I armed myself with a multimeter set to check the continuity and went through the whole schematic, verifying for each connection if it was replicated correctly on the PCB. And so for each connection between two components on the schematic, I verified with the multimeter that the same connection was also present on the PCB. And to avoid going multiple times through the same connections, or even forgetting to test some of them, every time I successfully verified a connection, I highlighted it on the schematic. I stopped only once I tested all possible connections. And apparently I was right in doing so, because I ended up finding a couple of issues. The first issue is a mistake on my side. While drawing the schematic, I didn't realize I missed to identify a cross connection of two wires, and so that cross connection was missing on the PCB too. I fixed both the schematic and the PCB design, and I posted the new Gerber files on the eleneasy.com page dedicated to the Synth project, and so you can order your own PCB with no errors in them. However, since there was only one missing track on the PCB and since it was a short one, I decided to fix my own PCBs with a simple wire rather than ordering a new one. And you'll see that being done later in this video. The second issue is a problem related to the silk layer of the PCB. This one is caused by an error in the library of the design tool I used that wrongly identifies the cathode and anode of the particular zener that I used for the voltage reference. Because of that, I wasn't able to fix the problem. However, it's just a problem in the silk layer, and knowing that, we can still connect the zener diode correctly. We just need to remember that we need to switch the position of cathode and anode. I put a file in a zip archive to make a note of the problem, and so you won't forget that when you build your own VCO. The file is named Important Note on PCB, so you won't miss it. You can see how I noted the two issues on the PCB itself using a marker. The assembly of the components on the PCB is very straightforward. Just remember some simple rules for it and you will be good to go. Start first with the mechanical components, in other words the sockets of the ACs and the power supply headers. I used two pieces of pin header in particular for the big socket of the SSI2130 breakout board rather than a real socket. The problem when installing these components is to keep them in position while you do the soldering. There are different ways to do that, you just need some imagination. For example, I normally use a piece of masking tape to keep the components in place, but recently I found another way which I think it is even better, which I noticed in the videos of two other YouTubers. There is this kind of blue putty, similar in consistency to the Play-Doh, that was designed to hold things together, like light frames on a wall or two pieces together while gluing them, and so forth. And there are several manufacturers that offer it, each one proposing their own name. I found on Amazon one from Loctite named Fun Tack. You can see how easy it is to stick it on the component and the PCB to hold the two firmly together while doing the soldering, and then it can be removed as easily. Very nice and useful and less messy than using masking tape. When you assemble the IC sockets, make sure to respect the position of pin 1. Once you install the socket, you won't see any more of the picture on the circuit layer, and so you have to make sure the socket is oriented correctly, because that will be your only reference to insert correctly the IC into the socket. After soldering all the mechanical components, I started soldering all the resistors. I usually do it in groups, inserting in the holes a number of resistors related to the same part of the schematic, and once they are all inserted, I solder them from the other side of the PCB. After soldering all the components, I cut the excess of their leads. To hold the resistors in place when I turn around the PCB, I usually bend their leads a little bit so they cannot slide out of the holes. Once one set of resistors is done, I move to another set until all the resistors are assembled on the board. After the resistors, I started assembling the trim pots. In this case we have 3 of them, all multi-turn. One is for the voltage reference, the other 2 are for the tuning of the exponential curve of the control voltage converter. Make sure you leave the cursor trim pots at about a halfway of their range to make it easier for the final tuning, which we will see in a later video. Next set of components were the capacitors. I started connecting all the filtering capacitors for the op-amps. I inserted all of them on the PCB and then I soldered them. They all have the same value and are used to filter out noise, both incoming and outgoing, at the power supply pins of the ICs. And in fact, you might have noticed that they are connected very close to those IC pins to reduce to the maximum possible extent the resistance of the conductors between them and the pins. Once done with the regular capacitors, I connected and soldered the electrolytic capacitors. Be very careful with those, make sure you connect them properly. They are polarized components, and if you put them the other way around, they will not work correctly and you may find that they could actually explode. Don't worry though, the explosion is messy, but not dangerous, at least for the capacitors used in this circuit. Each electrolytic capacitor has actually a weak point on its top created on purpose. That causes the metal case of the capacitor to break right at that point and release the internal pressure without causing too much trouble. But you'll see fumes coming out of the break point and possibly also some fluid that eventually will need to be removed with some alcohol to avoid over time corrosion of closer components and tracks of the PCB. Notice how once I finished soldering the capacitors, I also connected a wire to replace the missing track on the PCB. You won't need to do that step, since the driver files I'm providing you have been fixed and don't have that error anymore. Once all the passive components were soldered on the PCB, I started working on the solid-state components. All of them but the ICs. I worked first on the 4 LED. Remember that these components are polarized and you need to respect their polarities if you want the circuit to work correctly. The circuit drawings on the PCB help on that. You just need to align all the flat ridges of each LED to its representation on the circuit layer drawing. Once finished with the LEDs, I soldered the zener in its place. This is another polarized component and needs to be inserted in the right direction. Just remember that the band of the zener diode body is on the opposite side of the band drawn on the PCB silk. Unfortunately, I wasn't able to fix that on the PCB because it was really a library problem and I didn't want to mess with that. I could have actually used a different library element, but they only had higher power zener diodes in their list, and I didn't want to waste any space on the PCB, so I left it as is. Just remember that the polarity represented on the PCB is the opposite of the actual zener diode polarity. In order to tune the trim pots correctly, we will need to insert the ICs in the sockets in a certain order after all the connections are completed, and so I left this part for the last. So at this point, I started preparing all the cables needed to connect the components on the panel to the PCB. I had to deal with different sets of cables, depending on their use and their kind of signal they have to carry. I started preparing the cables for the 5 potentiometers that control the volume of the 5 mixer channels. These cables only need to carry a DC voltage, since the channels are handled with VCAs and the volume is adjusted through a control voltage. I therefore cut 3 pieces of flexible wire for each potentiometer, using 3 different colors to easily identify each lead of the potentiometer. I also make sure to use the same color for each of the 3 leads of all the 5 potentiometers. To reduce the clutter, I knotted together each group of 3 wires and used some shrinking tube at the 2 ends to keep them firmly together. I also prepared the same way all the other cables that will carry only DC voltages, plus the one carrying very low frequency voltages, since those are still control voltages that are practically unaffected by noise. Another set of cables is for connecting the input and output jack sockets carrying audio signal with the PCB. Because the audio signal could be affected by noise, I decided to use pieces of shielded audio cable to reduce the chance of electromagnetic interference. So I cut to measure all the pieces I needed, and then I prepared their ends to save time later, once I have to connect them to the PCB and the jacks on the front panel. Once all the cables were ready, I started soldering them on the PCB side. The other side will be connected later once the PCB is in place in its case. Since all the cables were already prepared, soldering them on the PCB was fast and easy. And like I did for the passive components, I proceeded by connecting similar groups of them, starting from those for the mix of channels control voltages. See how once all the wires were connected to the PCB, things started looking relatively ugly. Think of what would have happened if I left each wire on its own, instead of ordering them together in cables. Here is a view of how the panel will look like. On the top row we have the graphics for the 5 potentiometers that control the volume of the mixer channels. The 3 on the right control the volumes of the pulse, triangular and ramp waves. The 2 on the left control the volume of the 2 auxiliary outputs. Underneath the potentiometers we have the sockets to insert an external control voltage of the volumes, which could come for example from an envelope generator. When a jack is inserted in one of these sockets, the corresponding potentiometer will be excluded. Below the sockets there are 3 more sockets. The 2 on the left are inputs for the auxiliary channels. We will be able to add in there an external audio source or even one of the other waves produced by the same VCO. The socket on the right is instead the output of the mixer, from which the signal can be taken to go to other modules of the synth or directly to an external amplifier. The big blue dot on the center is the one for the transposed multi-turn potentiometer. The row below the transposed potentiometer is made all of sockets to enter control voltages. The 2 on the left are for the frequency modulation and for the sync. The 3 on the right are the exponential control voltage inputs to regulate the frequency emitted by the oscillator. Below the FM socket there is another potentiometer to control the depth of the frequency modulation. See how that is represented by the black line connecting the socket with the potentiometer. On the bottom row we have the input for the 5 signals generated by the VCO. The rightmost socket is associated to another potentiometer right above it that controls the duty cycle of the pulse, also known as its width. This drawing will be printed on decal paper, similar to the one I already used for the power supply modules. Once the drawing is printed, I will protect it with some transparent paint, so I can submerge it in water to detach the film from the paper. We will see one more time how the procedure works once the panel is ready to accept the decals. For that, I will need to sand it with fine grain and paint it in white, the same color I used for the power modules. Let's just say for now that I will not transfer this whole diagram at once. I will rather cut it in smaller pieces to make it easier to apply them to the panel. And, once they are all set and dry, I will spray some transparent and glossy paper on the panel to fix everything in place. This, however, is going to be the subject of the next video. In there we will prepare the panel, we will shield the back of the panel with copper tape, mount all the components in it, and then mount the PCB in the case as well. Lastly, we will complete all the wiring between the PCB and the panel. I'm not sure at this point if I will also be able to put in the video the tuning and the final test and installation of the VCO module in the rack. If not, that will be the subject for yet another video. With all this in mind, I give you appointment to the next episode, and I remind you to subscribe and click on the notification bell if you haven't done so already to avoid missing the next episodes. See you in the next video, and as usual, happy experiments!